This protocol uses gold electroplating and atomic layer deposition methods to create novel nanopillar-based split-ring resonator metamaterials with nanoscale gaps. Each fabricated split-ring resonator consists of thousands of gold nanopillars and is driven by displacement current across the nanogaps between them, which excites terahertz resonances. The magnitude of displacement current is proportional to the size of the nanogaps. The size of the nanogaps can be tuned by changing the cycles of the atomic layer deposition process, which results in changes to the resonant frequencies and amplitudes. An enhanced quality factor of approximately 450 can be achieved, which is 40 times more than the quality factor of 11 that can be achieved by thin-film split-ring resonators. A frequency shift 17 times larger than that of thin-film-based resonators can also be observed. Both simulated and measured transmission spectra demonstrate that the nanopillar-based metamaterials are ideal candidates for high-sensitive sensors and frequency-agile terahertz devices. Analytical results from scanning electron microscopy show the fabricated nanopillar-based split-ring resonator, 2 adjacent gold nanopillars, as well as the 10 nanometer aluminum oxide gaps between them.
Nanopillar-based split resonators contain gold nanopillars and 10 nanometer aluminum oxide gap. This structure excites inductive and capacitive resonance via displacement current that provide more energy storage. Enhanced energy storage leads to high quality factor and large frequency shift. Because of the high Q value,